Okay, welcome back. And I guess I just mentioned this in the video because I talked about this during the break so that you know what we talked about. So I was mentioning about this model called ADA boost and gradient boosting, which is I guess one of the popular, I guess nowadays one of the most powerful tree-based model. So in any of this, so ADA boost and gradient boost, the trees are actually learning from one another. So that's a concept called learning. So when you learn something, you're going to have something called learning rate. So this parameter is also another important parameter when you use any type of gradient or ADA boost model. So learning rate adjusts your learning from tree to tree. Okay, so apart from the depth of the tree or number of the trees, which is n estimator, do experiment with learning rate. Okay, if you were to do normal project, small data to medium sized data, I think ADA boost and gradient boost from scikit-learn should suffice. So because two of this, you don't need to install anything separately. Everything comes from sklearn. But once your data get to large data, or you have special requirement like complex data, or even performance issues, then you might want to consider like the kind of like the state of the art tree models nowadays. It's called XGBoost, CatBoost, and LightGBM. So all of this required a separate installation. So you just do pip install and then followed by the name. I'm not going to go through this in this model, but these three are pretty much the most powerful, I guess, tree-based model nowadays, and I've seen people use a lot in the paper. So if you want to do this, I guess come talk to me. It's a pretty complex model, but it's quite powerful. Okay, that's all I want to say. All right, so let's move on to the last regression model that we're going to learn in this course, which is K nearest neighbor. K nearest neighbor regressors. Okay, so again, the nearest neighbor is actually the model that you don't need to train anything. There's nothing to train because it's actually drawing the conclusion from the neighbor in your data itself. Okay, but this one it's actually predicting the number instead of predicting class. Okay, so let me show you how it works. It's pretty simple actually. Okay, so again, when you use the K nearest neighbor, there's no training. So this is the data that you're going to use to predict something. There's no training at all. There's no weights. There's nothing in here. Just pick. So first you're going to choose the number of your neighbor that you want. So n equal to 3. Okay. And let's say that you want the K nearest neighbor model to predict what's going to be my y at x equal to 10. Okay? So first, it's going to look into this x equal to 10 right here. Okay? And then it's going to find the nearest data points from x equal to 10, which is going to be this guy, and this guy. So the nearest data point, meaning the nearest data point along the x-axis. Okay, so you look left and right and in the middle too to see if you have any data along the x-axis that are closest to wherever you want to predict. Okay, so you got these 3 data points. Okay, and once you got these 3 data points, you got 3 y values, right? For example, you got this, I guess, for lack of number, just 1. I don't know. Maybe this one should be 2. You have y. Maybe I should see y2, and then you have y3. So like that. So essentially, from your 3 neighbor data points, you have 3 y value. And if you want to predict the value, the corresponding value that you want, you just take the average of that. So take the mean of that. Okay. So that's it. That's how it works. Okay. So essentially, I'm taking the average of the y values of these 3 neighbor points, which I end up to be this guy right here. Okay, I know it's kind of confusing because it take me a couple tries to wrap my head around this. So let me show you what happened if I were to choose another x. Okay, let me show you this. Okay, if I were to choose, okay, let's predict something at x equal to 5. See what happened? Okay. So first, I'm going to look, left and right to see if I can have 3 neighbors that are closest to me. So I guess my 3 neighbor would be this guy right here, closest along the x-axis. Okay. Another one would be this guy. Another one would be this guy right here. Okay. From this guy, right, from this 3 neighbor, closest to x equal to 5, I get this y right here, y1, guess y2, and I get y3. Okay. And I'm going to take the average, so mean of that value. So I would suppose that my average would be something like, I don't know, like here. Okay, y prime. Okay. So that is the prediction at x equal to 5, like here. So that is how k nearest neighbor is going to predict. That's it. So it's very, very simple. Okay. I don't know if you need another example, but if you need another example, let me know. Okay. All right. So that's it. That's how it works. Okay. So as you can imagine that I guess the number of neighbor is probably going to affect your prediction the most, right? Because it depends on how much you want to average over, right, your neighbor. But here's the thing. There is what if you are x equal to maybe 20? Like what happened here, right? Because you only have your neighbor along your left side, but nothing along your right side, right? If you guess that it's going to pick things on your left side, you are guessing correctly, okay? So if there's nothing on the right side, you're gonna keep picking things on your left side, because that's the closest neighbor you can have. So as you can imagine that the k nearest neighbor is probably not going to perform well if you are predicting something along the edge, because you don't have anything to the right side. Or similarly, if you want to predict something on the left side and you don't have anything here, then your prediction is going to base on something on the right side, which is probably not going to be the best prediction. Okay? So I guess for a k nearest neighbor, or I guess any machine learning model, if you try to predict something outside the training data range, probably not recommended. Okay? And also, if you change the number of neighbor, then it's also going to change how the prediction is going to be. So the effects of your neighbor is that if your neighbor is small, that means you're going to try to stick closer to the data, because you don't have much things to average it with, right? But once your neighbor is large, that means that the average effects will be more pronounced. So that means that your prediction will be, less sticking to the point, but more like averaging, or more, less curvy or less jacky, right? Less jagged, but then like more averaging in terms of the shape. Okay. All right. So let's see what it's doing in our example, shall we? I'm going to go to my k nearest neighbor, and let me just do another file, C1. Okay. Actually, you know what? I'm just going to show you this file because it's the same. Like everything else is the same. The only thing let's change. Wait, why does it say random forest? Okay, I think I made mistakes in here. So this one should not be random forest. It should be k nearest neighbor, because I downloaded from here. I mean, this is what I imported. Okay, so this one is wrong title. Sorry. Okay, so the only thing that changed is I import this k neighbor regressor, and then this one is the loading of the data, extract the data, and split the data. Okay, and this one again I construct the parameter sets again. I'm doing the okay. So this one I think I try to do a lot of numbers, so that's why I use the 2 loops in here. So let me show you this one. Okay, in here, so first what I do is that I want to construct an array, and I'm too lazy to type it in myself. So I want to construct array such that I have the odd number. So 1, 3, 5, 7, 9. So see how lazy I am. So I mean, technically I could just write it in myself. Like I could just type it in manually, but I'm too lazy. So I just do a loop like this. Because, you know, I can change it to be 40 and then it will just increasing the number automatically. So yeah, I'm lazy, okay. So that part construct the array of the neighbor. And then the rest is the same because I'm constructing the dictionary that contains the key, which is the experiment number, and also the parameter, which is n neighbor. Okay, so let me just show you this. Okay, so in here, I'm going to change the number of neighbor from 1, 3, 5 to 19. So that's a lot, right? And let's see what happened. Okay, so the rest is the same. This one, identical code. I didn't do anything else except from changing the model. So let's run it. Okay, as you can see that when n, so the first, I guess the one on the top are the one with less neighbor, and the one on the bottom is the one with lots of neighbor. So as you can see, the averaging effects working in here. So when you don't have a lot of neighbor, this is n equal to 1. So it's sticking to the training data pretty well, but probably not good in terms of the test data, right? When you start to increase the number of neighbor, then the averaging effect kicks into operations, and you can see that yeah, it's getting better, right? As you increase the number of neighbor, then it starts to average more and more, and I feel like this one seems good, you know. Even it's still a lot of jacket shape, okay? But once you increase the neighbor even more, then maybe it starts to average too much. I don't know. I'd have to look at the results, right? Go back to the results. And you can kind of see that, yeah, actually, no, it's actually doing pretty well. So again, this one should be a red flag to you, right? If it's fitting too well to the training data, but not with the test data, then this is overfitting, okay? But once you start to fit, you know, less well, but then you increase the test accuracy, that means that you're going on the right path. So the number of neighbor that I think might be okay, it's maybe around here, maybe 10 to 11. It's still overfitting a little bit because you're still fitting the training data quite well, but not too much. But if you recall, 0.65 is something that, you know, along the top performer, so like a support vector machine or a random forest can provide this type of performance, and also k nearest neighbor. So this is something that you can use if your data is not too much, and this is a very lightweight. I guess it's lightweight in terms of there's no training, so you don't waste any training time at all, and it still performs quite well, I think. Okay. Okay, so for k nearest neighbor, there's not much to change except from the number of neighbor. So I mean, you can try more, but I feel like this one is pretty inclusive enough. Like if you feel adventurous, you can get more. Like maybe I can show you, I can go to maybe 40, but then I want to increment maybe 4 at a time. So if I run this, see what happens. Yeah, so 40 neighbor. So it's averaging a lot, and in the end, you probably get something. So actually, still doing pretty well with the 37 neighbor. So it's actually not bad. So I would say that it's in this case it's quite robust in terms of like the number of neighbor. But you should probably not go too further than this. Okay. Okay. All right, so we've been through a lot of model, right? And then each model, you have lots of things to try it on. But I mean, I guess the last question would be like, if you were to do this in your studies and you want to try everything, like what would you do, right? So I have including one last notebook as an example. So this one is called Combine. So the Combine is pretty fun because now I want to show you how to combine all different types of model, and within each model, you can change the parameters too. Okay, So let's look into what I did here. So first, I need to import everything here. So linear regression, rich lasso, elastic, elastic net, support vector regressor, decision tree, random forest, ADA boost, gradient boost, and k-nearest neighbor. So as you can try everything. So it's pretty easy in here. And I load all the models in here. And then here is where I set everything up. Okay, as you can see that because I'm changing the model, so that's why I need another key called the model. And this one, I just use the class definition. So notice this one is not even the instance of it. I'm just using the definition. I will instantiate it later. Okay, but within each class, I can say that the parameter is something in here. So for example, for rich, I want to change alpha, right? For SVR, I want a kernel to be this, like that, okay? And you can come up with more things in here. I will show you how to come up with different type of parameter per model. But again, I can have different models, and within each model, I can do different parameters. And the way that I would do this is that first, I want to loop with all the model. So M is the item in all this array. So M is one of this dictionary here, okay? And then from this, I can extract the model and the parameter out, whatever I define above. And then here, once I have the model, so notice that the model is the class definition. So I need to instantiate it for example, just call it, right? And injecting all the values into here. Once you get the model, everything else is the same, like fitting, predicting, store results, and also plotting everything, okay? If I were to run this one, you can see that now I got all the models with all the parameters that I want here. Pretty good, right? And I think this one, I think what I did is that I collect, the best parameter that I can find from each of the models that we learned and put it into the same sheet. So as you can see that we go from straight line, right? This is the linear model, through the straight line with regularization. So this is rich, I think, rich and like elastic net, things like that, right? So still straight line. We go to SVR, so this one support vector regressor with the RBF kernel, so it's non-linear, right? And to the decision tree, to the random forest, right? And this one to ADA boost, right? Gradient boost, and then k-nearest neighbor. So everything that I collect from here. So and you can kind of see the performance that it's doing, right? If you were to look at the R-square test, you can see which one's the best, I guess, from our matrices. The winner, I don't remember which one is, but the winner is the random forest. Okay, yeah, something like that. But again, I haven't explored with all the parameter, right? So maybe I encourage you to change more things. Okay, so the way that you would change something like this is that you can just copy. Let's say if I want to experiment with SVR, right? I want to copy like this. Just do another items in here, for example, yeah, like that, right? But I want to change C to be 100, like that. So, and that's it. Now I have even more things to experiment with, and I run everything, and now I should have even more stuff to work with right here. See, I have SVR, right? And this one actually performed even better, right? Something like that. So that's how you would like construct your, I guess, your experiment, like automated runs, so that you don't have to keep typing things. Like the way that if you find yourself changing things every time you run, stop and make things into an automated test like this, and it will make things much easier when you like make reports and make sure that you don't make mistakes and rerun things when your advisor asks you to change something, which can happen a lot of time, right? You can just rerun things pretty easily, okay? Okay, so maybe spend a couple minutes, maybe like adding things into here, changing things in the model sets, right? And then try run it to see, like what the things are changing, and then you can kind of experimenting with, like see the results and things like that.